Hi everyone, good morning. Let me share my screen first. Um, so I believe my screen is now shared. Okay. Hi everyone, good morning. Welcome to the Firebase Cloud Firestore Talk. Um, my name is Arnelle. I'm at Arnelle Balane everywhere on the internet. I write code at Logic, and I'm also a Google Dev expert for web technologies. I'm also part of a YouTube channel called Uncut Exception. We do a live stream every Saturday to talk about random various programming related topics. So please subscribe to our channel. That will help us a lot. Okay. So for this talk, we will be covering these topics. First, we will cover how to structure the data that we store in Cloud Firestore. Then how do we secure that data with security rules? And finally, how to test our security rules using Firebase Emulator Suite. Uh, so let's just get right into it. So first, structuring our data. Firebase Cloud Firestore is a NoSQL document store. It's unlike relational databases like Postgres or MySQL, where data is organized in tables where each row represents one entry of data. Firestore is different. Data uh, in Firestore are called like documents, and they are organized into collections. So in Firestore, there's no like strict schema on what fields or what your data looks like. You can basically structure your data however you want. So we'll take a look at different approaches to structuring our data. So there are primarily three ways to like organize our data in Firestore. First is to just store the data in the same document. Second would be subcollections. And third are separate root level collections. Let's take a look at them one by one. But before we do that, there are some things that we need to keep in mind when using Firestore. First is that documents have limits. So every entry of data that we store in Firestore has limits. So that would be each document can only be 1 MB in size, and also have a maximum number of 20,000 fields. That's a lot, but there's still a limit. Second is that queries are shallow. So when you have collections and sub-collections, when you try to fetch or read a document from a collection, it doesn't include the documents in that document sub-collection. So that's what it means. That's what shallow queries means. Third, we can't retrieve a partial document. So if we want to get a document, we get the entire document. We can't specify which fields of the document we want to fetch. We will fetch the entire document. And finally, we are billed by the number of reads and writes that we perform. So there are also other factors that affects billing, like the size of data stored, the network bandwidth stuff. But for most of the time, reads and writes, it's what we need to keep an eye out on. So keep this in mind while we now or in the future when you use Firestore, structure your data when we first start. So for this talk, we'll assume we have this sample application. So it's an app, could be a web app, could be a mobile app, because Firestore supports both. So that lists coffee shops, for example. So we have a page that lists all coffee shops. When you click on one, you go to the detailed page where you see information about that coffee shop, as well as the top 3 reviews for that coffee shops. So let's just pretend we have this. So how do we structure this data? So let's try the first approach, store the same document one. This is very straightforward. That just means that in one document you store all the reviews inside it together with the coffee shop information. So if you're already thinking this is not a good idea, then you're right. This is not a good idea. Uh, if you think about it, there's one little upside to this, which is you only need to do one read. By doing one read, you get all the data already, but there's a lot of downsides that outweigh all that one tiny upside. So first is because reviews can be a lot, right? So let's say a coffee shop is very popular, it has a lot of reviews. The reviews map here will keep on growing and it will easily reach the document limits that we talked about earlier. It will easily reach 1 MB or 20,000 fields. So this is not good. Second thing is when you just want to fetch one coffee shop, you automatically fetch all the reviews for it, even though you won't need it, because we cannot read partial documents. If you want to get the document, we get everything inside that document. So we can't exclude reviews. So that's a lot of wasted bandwidth and data that the user will see. Third, it's difficult to perform queries on the reviews. If you want to do things like get all reviews written by Arnelle or get the top 5 reviews, if you want to do that, we can't do that using Firebase queries. We have to do that on the client, like on the web app or the mobile app. So this is not a good idea for data that keeps on growing. So let's take a look at the other approaches. The next one is separate level collections. It basically means that we have a collection that stores all coffee shop documents, and we also have a collection that stores all reviews documents. And each review can have like a field representing, storing like the ID of the coffee shop that it was written for. So sort of like a foreign key in relational databases. So this works if you want to get if you want to list all the coffee shops, you only need to get information about that coffee shop because that's all that is stored in the coffee shop document here. But if you click on a coffee shop, you need to fetch the reviews. And that's also easy to do. You can just query the reviews collection, filter them where the shop ID is um, the ID of the coffee shop that the user is viewing, and then you get it already. And it's also easy to do queries that involves all reviews. For example, if you want to query for all reviews written by a particular author for any coffee shops, that's easy to that query is easy to do if we structure it this way. So this is an improvement already compared to the previous one. One thing to keep in mind when structuring data like this is that if you want to query, for example, in our sample app, if we want to query all reviews of a coffee shop sorted by date, for example, or sorted by like score rating, um, we're going to need a composite index. We'll talk about composite indices later. So just one thing to keep in mind when you're structuring it this way. So next, take a look at subcollections. So subcollections, similar to root level collections, except each coffee shop document will have its own reviews subcollection. So all reviews for, let's say, Starbucks, for example, will be stored in Starbucks reviews collection. So one advantage of this is if you want to query for all the reviews for a particular coffee shop, then you just query directly on its associated subcollection. So we don't have to do composite indices anymore. Another thing to keep in mind with subcollections is if you want to perform queries that involve all the reviews. For example, again, if you want to get all the reviews written by a particular author for all like restaurants, so that would involve querying all these review subcollections. To do that, we need to perform a collection group query. So basically, there's like a trade-off, whichever you use with subcollections or separate group level collections, but it's not really bad. You just need to know about it so you can do it when you need to. So this is how we would structure our reviews information. So for this case, we will go with sub-collections because um, in our sample app, for example, we won't really need to query across all reviews. Most of the time we will query all the reviews for a particular coffee shop. So we'll stick with sub-collections. So going back to like storing everything in the same document, It's not also entirely useless. So there are cases where it would make sense. Oh no, it's not it yet. So another use case for sub-collections is if you want to do access control. Take for example, in our coffee shop example, coffee shop we want certain users to be able um, to edit the coffee shop. So that maybe they are the employees of the coffee shop, you allow them to like edit information about the coffee shop. So in our case, we might have an editors array in our coffee shop document. So together with the other coffee shop information. So this editors array can contain the user IDs of the users that you want to be able to edit this coffee shop document. So that works. It's easy because every time the user access a coffee shop, we can just check if that user's ID belongs in the editor's array, right? And then give them access or not. But there's also like, I mean, yeah, definitely that works. But there's one downside to that. That would be every time you fetch or the coffee shop, for example, in the list of coffee shops, we are leaking the editor's array also. So this the list of users that you want to edit a coffee shop, you don't necessarily want like everyone else to know who has access to this coffee shop. So and we cannot exclude this information because we cannot read partial documents. If we get a document, we get everything inside that document. So this might not be the best way to store uh, private information like this, such as who can edit this document. So what we would do is we can store that private data into its own sub-collection again. So each coffee shop document can have like the reviews, which stores all the reviews for that coffee shop, and also another sub-collection that stores like private data about that coffee shop. So could be like who can edit this coffee shop and other like private information if we want. Then we can write security rules to prevent access to this sub-collection. See that later. So yes, this is another use case for sub-collections. Okay, so moving back. So when would we need, I mean, when would be like a good use case for storing information into the same document instead of sub-collections? That would be when you have information that most of the time needs to be displayed together with your main document also. For example, here we have a coffee shop detail page. When the user clicks in a coffee shop, we see the top 3 reviews, right? Uh, so this is not, even though the coffee shop has like 1,000 reviews, we only display the top 3 reviews. So what would happen? So currently our reviews are stored in a sub collection. So if we want to get the top 3 reviews for a coffee shop, we have to query the sub collection every time. So like get, let's say, sort by like rating, then get the top 3, and then read those 3 documents. So, but we have to keep doing that every time the user visits this page. For example, the user goes back to the home page, clicks on one coffee shop, then read 3 reviews, and then goes back to the home page, clicks on another coffee shop. We need to read 3 more reviews again for that new coffee shop. So this reads for the top 3 reviews can add up into a lot of reads that will incur like some reading charges. So one way to optimize this is to just store the top 3 reviews directly on the same document, like this. So in our coffee shop document, we have the coffee shop information, and then we also have a field for the top 3 reviews, which will contain just enough information that we need in the UI. So we don't need to store um, everything about the review, like when it was created, things like that, if we don't need it in the UI. So just enough information that we need in the UI. And yes, if you're thinking if this is duplicated data, yes, this is duplicated data based on the reviews sub-collection. But that's a thing with um, NoSQL databases in general. So with relational databases like Postgres, MySQL, um, we're like trained to like normalize our data, right? Data should be stored in one place only and then just do joins and everything like that. But with NoSQL, it's common to like duplicate data like this so that it's faster in terms of like reads. So with this structure, with the top three reviews stored directly in the coffee shop document, every time we open a coffee shop, we don't need to do 3 reads anymore to get the top 3 reviews because the top 3 reviews are already included when we read the coffee shop document. So that's 3 reads less than before. So this is one use case for storing information in the same document. Another use case would be if you have um, like for example, in our app, we have like a feature where the user can select their favorite coffee shops. So for example, they can click on a star somewhere, then it will be marked as their favorite coffee shop. So one way we will structure that might be just store favorite coffee shops um, field in our in our users collection. So every user has a user document which contains um, information about them, and you can just add favorite coffee shops field, which stores like the IDs of the coffee shops that you have favorited. So now again, you're thinking here, what if the user favorites like 1 million coffee shops? Yes, if that's a possibility in the app, then this would be not a good structure. So we would move it into its own collection. But depending on the app, for example, in this case, we only limit the user to have like maximum of 30 favorites. Otherwise, what's the point of having favorites? So let's say user can have maximum of 30 favorites, and that's fine. We won't reach the limits for each document. Then putting them directly in the user document is all right. Okay, so those are the 3 things. Different ways to structure data in Firestore. We mentioned composite indices earlier, so let's talk about it now. So everything in Firestore, like, so remember Firestore, each data is called a document. It's like it looks like a JSON. I think it's literally JSON also. It's like a JSON object, like fields and values, and then they are organized into collections. Um, in Firestore, every field in a document is indexed. So a database index is basically like a sorted list of all the values for that field, and then associated with like its location in the database, so that indices actually make queries faster even with relational databases. In Firestore, every field is indexed. That's what makes Firestore queries really, really fast. Even if you have like millions of records in your Firestore collection, um, reading data from that collection will always be fast because everything is indexed. However, Firestore indices by default are only like single field indices. So if you want to perform a query that involves multiple fields, for example, get the coffee shop with a specific name and also order the results by like the created date, the coffee shop. We're dealing with 2 fields here already, and Firestore doesn't automatically have the index for that, so we have to create it ourselves. So we have to create a composite index ourselves. So we can easily do that in the Firebase console. So in the Firebase like web console, there's there's going to be a tab called indices, and we just create an index. So which collection, and then the fields that we need to create an index for. So here create a name and create that. So this is like the manual way of creating indices, and I don't really like this. It's too much work. So another alternative approach is just to run the query. So the first time we attempt to run this code in our app, this will not work because the composite index doesn't exist yet. But if you look at our console or whatever is used for like mobile development, there's always going to be a console somewhere. There's going to be an error saying that there's no index for this query. But if you look closely in the error, there's going to be a link that we can click, which will automatically create the index for us. So clicking on this link will redirect to the same like Firebase console, but the fields and the index like configurations are already defined for us. So just click create index and the index will be created and our query will now work. So that's composite indices, basically just indices that involves multiple fields. Another thing we mentioned earlier is collection group query. So it's when we want to perform a query that involves multiple collections, especially useful when we want to do a query across sub-collections, like our reduce sub-collection. So nothing's different here actually. So if you're familiar with performing Firestore queries on a collection, it looks exactly the same, except we do firestore.collection group. Then this will automatically perform the query on all collections that um, that are named reviews. So that's collection group query. Collection group queries also require a composite index, but following the instructions before, you can automatically create them from the link in the log. And that's it for like different ways to structure data in Firestore. Just to summarize, there are three ways. One would be storing the information directly on the same document, which is useful when there are like data that most of the time we want to display together with like the same document, like the top reviews and stuff like that. This is not good for data that grows or doesn't have a fixed number of items. Like reviews, we can have a lot of reviews, so don't store them in the same document. Subcollections is also another way, which is a collection that is nested under one document. This is useful for like one-to-many relationships of our data, such as like coffee shops and reviews. And the third approach is separate top-level collections, which is usually useful for like many-to-many relationships. So now that we know how to store and like structure our data in Firebase, let's now go into how do we secure them. Firestore and Firebase in general, and that's done using security rules. Security rules, okay, if they look like this in the Firebase console, there's going to be a tab says rules, and then there's the default rules. Security rules basically allows us to define like custom logic on how on it allows us to define logic on like for each document who has access to those documents. So if you want to get a coffee shop, you can access that coffee shop, for example. So in the Firebase console, in the rules tab, we can edit our rules directly here. So this is a simple example. Let's take a look at a more like populated example already. Rules are structured like this. So it's composed of like match blocks. So each match accepts a path. So if the path to the document being accessed matches this, then this security rule will be evaluated. We can nest match blocks inside each other, like to simplify like the paths here. So let's take a look. So here we match coffee shops, which I misspelled. So for this means for each document inside the coffee shops collection, we allow anyone to read it, meaning getting or querying coffee shops is allowed. But here we have allow if false for write. So meaning no one can update or create or delete coffee shops. So it's the syntax basically. Same for private data and reviews. So allow, read or write, they accept Boolean values. So if false or if true or any expression that results into a Boolean value, which will be in the next slide. Or not next slide. Read, there are 5 operations that we can write security rules for. That would be get, list, create, update, delete. So like basic prod operations. Get and list. Get is for getting like one document. List is when we want to query multiple documents. Create, update, delete, they're self-descriptive. Get and list here, if you want to write security rules for both, they can be, that's what read means. Read means get and list, and write means create, update, delete. although most of the time we will find ourselves writing security rules individually for these queries instead of read and write. But these are handy shortcuts also if needed. So yes, aside from like simple like if true, if false security rules, a lot of the times we will have more like complex logic in our security rules. And there are some things that we can use in our security rules to like validate the request. First thing would be the request data. So that's like the incoming request. Here we can get information about the user making the request and like the payload or like the data being sent in the request. Second would be the target documents or like the document that we are trying to access to or like the document that we are trying to protect with our security rules. And then finally, some other arbitrary document somewhere in the database. So let's go through them one by one. First would be the request data or the incoming request. Um, one common information we access from the incoming request is request.auth, which represents the current user making the request. So here we can check, we can like allow or deny certain requests depending on who is making the request. We can check if like the user is logged in, for example, in order for them to create a coffee shop by checking if request.auth is not null. And we can also check specific information about the current user by checking like their claims, like the token, or like if their email is of a certain pattern, or if their email is verified. And we can also check the user ID, which is unique per user per Firebase project. So if you want only a certain user to be able to access like certain information, then we can write a security rule that checks directly for that user ID. So it's something like this. So there are more things in request.auth. Um, we won't be able to cover everything now, so I suggest you refer to the Firebase docs for request.auth. So another common thing to check in the incoming request is the payload or like the data being sent in the request. So this is usually useful to perform validation of data. So if, for example, in our app, we might have a form for creating coffee shops. In that form, it's true that in that form, we can add our validations already, like the name should be a string, the location should be a string, and they're both required, but the length should be less than 100, for example. Uh, yes, we can do that in the app, but generally in like web development stuff, we never trust like any like request coming from the client because that can be easily like modified by the user. So most of the all the time we need to like perform server side validation as well, even though we're not using Firebase. Even though we have like a server side like a backend application, also need to write server side validations, right? But with Firebase, we don't have to write our backend anymore. We just have to write security rules to validate the incoming data. So here in our security rules, we can check request.resource data, which is the actual data being sent to Firebase, and then perform our validations from there. So here we only allow creating coffee shops if the coffee shop name and the coffee shop's location are defined and their lengths or size in security rules syntax is less than or equal to 100. And if it's not, then the request will be rejected by Firebase. So that's requested resource. And yes, so those are the two things primarily checked in the incoming request, the current user and the data being sent. The second thing that we can check in the security rules is the target document or the data already stored in Firestore that we are trying to access. So it can be accessed through the resource variable. So what's the difference between resource and requested resource that we just talked about earlier? So requested resource is like the data in the incoming request, right? It's not stored in Firebase yet. However, on the other hand, resource is the data that is already stored in Firebase. So that's the difference basically. But the structure is pretty much the same. So we can check, for example, what we have here. So for example, in our app, we have articles, and articles can be in like draft or published status. Published articles should be not editable anymore, but draft articles can still be edited. So we can enforce that through security rules by adding uh, a rule for like the update operation, where update is only allowed if resource that the status is still in draft. So here we are accessing resource, which is the data that is already stored, currently stored in Firebase, and we check if that document is still in draft. And if it is, then we allow update. Otherwise, we don't. We can also like um, combine this with request.resource or like other request, other information we can get from the incoming request. So we can do things like a review can be edited, but only the user who wrote the review can edit that review. We don't want other people editing our reviews, right? So we can enforce that by checking if like the user making the request, so that's request.auth, we check its user ID and compare it to the user ID that we have stored in the document already in Firestore. So request that data, that author ID, for example, could be a field here. So we can do things like that with security rules. So nothing really much to say about resource. It represents the data that's stored in Firestore that we are trying to access. And finally, another thing we can use in security rules is to check any other arbitrary document anywhere in the database. So this is useful for doing um, access control or other validations. So for example, we talked about this earlier already. We have a coffee shop collection with documents. Each document has a private data subcollection containing an editor's array with like user IDs on who can edit that coffee shop. So let's say we are trying to like perform an update on this particular coffee shop. So before we allow that or deny that request, we need to check private data, right? Which is like some other document in the database, not really the document that we are editing. So to get a document somewhere else in the database, it's like the private data here. We can use get or exist functions in security rules. So exist only checks if a particular document exists. Yes, that's the name suggests. Get actually gets the value or like the data stored at that location. So we can access its fields in our security rules. So in our case, we want to check if the current user is in here. So we are going to use get to get the actual data stored. So in our security rules, okay, don't be intimidated that it looks complex now. So let's try to break it down. So here we have our usual allow update check. So allow update only if. So here we get the current user's ID. So we already saw this earlier. Request a path, that's the current user. Get their user ID and check if that user ID is in the editor's array. So here we use the get function, we pass in like the path to the document that we want to check, and that is, so one caveat here is we need to pass the complete path, which I don't really like because it's too long. So here we pass the like, complete path to the private data, so that would be slash databases, the database name, whatever it is, documents, shops, and here we interpolate like the coffee shop ID, and then private data, and then the private document. So in Firebase, these values inside curly braces, they are variables that stores whatever the path is at that location, and we can use that in our security rules directly. For example, here we use $sign parentheses to insert that value in this path, for example. So once we get this private data document, this returns an object that looks like the resource object. So we can access that data, and then we can access whatever fields this document has already. So now, hopefully it's now clear that we are checking if the current user's user ID is in this coffee shop's editor's array, and if it is, then we allow the update. So only editors added to the private data of the coffee shop can edit this coffee shop. So and yes, so this if you look at this, things start to get complicated already. And imagine if your app grows, as you add more features to the app, you will be adding more security rules also for each of those collections that we add to Firestore. So that could get that would be that will make our security rules get like messy easily over time. So one thing we can like one way to like organize our security rules is we can use custom functions. So Firebase allows us to define custom functions in the security rules that we just call here. So instead of this, where we write our logic directly on allow update security rule, we can extract that logic into a function. So we call it user is coffee shop editor, then we do the same logic that we did earlier. And in our allow update, we just call our function directly. So this serves two purposes. One is that it gives us it allows us to give a name to the logic that we are trying to perform. So instead of reading like this code here, right, where request.auth of user ID is in editors, it still makes you think that, okay, what is this trying to do? However, reading user is coffee shop editor is more like we understand it easily. Later on, after 3 months, when we visit our project again, it will be easy for us to remember like what are we trying to check here. So that's first, allows us to name our logic. Second is it allows us to reduce repetition in our security rules. For example, in allow, if you want to add, if you want to add a security rule where only editors can delete a coffee shop, for example, we don't have to repeat this like complex um, logic anymore. We just do allow delete if user is coffee shop editor, so we can just reuse our functions. So that's custom functions allows us to reduce repetition and give a name to our security rules logic. And okay, testing as we edit security rules directly in the Firebase console. We want to know that they are working properly, right? That we are actually doing their job of securing our data. So in the Firebase console, there's a tool called the rules playground. It allows us to like simulate different requests and see if that request is allowed or denied by the security rules that we just wrote. So um, yes, so once we open the rules playground, we can choose different request types, for example, get or list or update, create, delete. We can pass in a location to a document that we would like to perform the operation on. We can pass like arbitrary data that we want. We can also set like the user status, like if it's the user authenticated, we can specify which user is authenticated. And then when we click run, the simulator will check um, if that request is allowed or denied based on the security rules that we just wrote. So it will show us which rules allow the request, which rules deny the request. So things like that we can do on the rules play. So just provides us an easy way to do a quick test if our rules is actually working or if there are errors and things like that. So that's it for security rules. They allow us to like write our own custom logic to secure, to control who has access to which data. In security rules, you can check either the incoming request or the document being accessed, or even some other document somewhere else in the database. And we can use the rule simulator in the Firebase console to test our security rules. Finally, go to the Firebase emulator suite. So Firebase emulator suite. Yes. Okay. I thought someone's going to. Okay. Firebase emulator suite allows us to run Firebase emulator suite allows us to run like emulators of different Firebase services locally. Um, for this talk, we focus on the Firestore emulator. So why would you want to use the Firebase emulator suite? Three things, basically, number one is speed. So because the emulator will be running on your local machine, our test won't be doing network requests to like the Firebase servers anymore. So there's no like network latency, everything will be fast. So that's speed. Number two is safety. We can write, delete, do whatever we want with our test data without worrying that we'll be messing up our production database. So because everything happens locally. And finally, it's cost. Remember, we appeal with the reads and writes that we perform. So if we perform those, if we have tests that does reads and write and then perform them on our production DB, we will be incurring like billing charges for those. But using the local emulator suite, they run locally. Um, so to pay for those. So using Firebase emulator is good for development. So how do we get started? First of all, assuming you have access to your terminal and then your laptop, you have the dependencies installed already like Node.js. We need to install the Firebase CLI. So Firebase CLI allows us to run Firebase commands. So first we install it as an npm package using npm install -g Firebase tools, and then once that's installed, it will give us the Firebase command. So first we need to log into our Firebase account by running Firebase login in our terminal. This will open the web browser that allows you to choose which Google account to use to log in, but it's just a simple login, so nothing complicated. So after you log in, inside your app, for example, whatever app we're building, we CD into it, and then we can run Firebase emulators. This will initialize the emulators that we want to use for our Firebase project. So here it will ask us to choose like which emulators we want to use. Uh, so for this example, we just use Firestore emulator. It will prompt us also for like different config stuff, like which port to run on, etc. For our emulators, most of the time we can just stick with the defaults. And once it will also take care of downloading the emulators for us. So here, would you like to download the emulators now? So yes. And once everything is initialized, then it will just tell you that it's done. And once everything is installed, we can run the emulators that we have by running Firebase emulators :start. So it will run the different emulators with your specified ports. This is what the Firestore emulator looks like. So yes, it also gives us a local web UI where you can access or where we can view like the state of the different emulators and the data stored in them. So this is the one for Firestore. As you can see, it looks like the actual Firestore UI on the web Firebase console. So yes, here you can interact with it just like it's the actual Firestore. You can clear all the data, things like that. Okay, but if we're like writing unit test, we don't really have to open this, but just showing this in case you're interested. So now we have the emulator set up. We can now run our unit tests locally. So let's try setting up some sample tests now. So to write our test, we install our like preferred like unit testing or like testing like framework and stuff. So for example, we use Mocha, and we also need to install the Firebase rules unit testing library. This will give us access to some utilities that allows us to use the emulator suite. So for our like unit test example here, let's just assume that we have a collection called read only, and we want these rules for this collection. We want to allow reading all documents, so everyone can read, but we want to prevent all writes to any documents in the read-only collection. So that's what makes it read-only. So we want to write security rules for these requirements, and we want to write unit tests that verify that these rules are actually working, and then run those unit tests using the local like Firebase emulator suite. So first, let's write our test. So in our test, we first load the Firebase unit testing library, and so we start defining our test. So this is how tests are defined using Mocha. It might vary depending on your testing framework. Here we define our test, we define each test case. So first test case is it allows reading data from the collection. Okay. And next is we initialize the Firebase app. So if you use Firebase, usually initialize, we usually call Firebase.initialize app and pass in all the configs for our Firebase project if we're using the actual Firebase SDK. But this is the Firebase unit testing library, so we call Firebase initialize test app. It will configure our project already to use the emulator suite, pass in our project ID, which we can get from the project console. And then that's the only difference compared to like using the Firebase SDK, just called initialize test app. And from the app itself, we can get reference to Firestore already. So we get Firestore, that app that Firestore equals app that's Firestore, and this will be using the Firestore emulator. And from there, we can write a test. So here our test, we want to check if reading data is allowed. So um, we try we try to do that and see if it's allowed. So we try to read a specific document from the read-only collection. So let's say doc1, and we do doc.get. That's how we do reads in Firestore, and then C, and then we do an assertion to check if that doc.get call worked or succeeded. So the Firebase unit testing library provides us with methods like assert succeeds, which will do the assertion for us. So assert succeeds make sure that the past operation provided operation succeeded. There's also assert that fails, which will make sure that the provided operation fails. So which is the case when we want to prevent writing data to the collection. So writing or calling doc.set, for example, should fail, and we want to check that in our unit test. So if you run it, running depends on your unit testing framework again. But if you run Mocha, it will show us that, okay, the first test passed, but the second test failed. We were able to write um, um, data into the collection, into the read-only collection. So we can fix that by editing our security rules in the file called firestore.rules. So when we initialize Firebase in our app by running Firebase init, and then we chose to initialize Firestore, it will generate a file called firestore.rules, and this will contain the security rules for our app. So the nice thing with this file and like the emulators is that every time we edit this file, the firestore.rules file, the emulator will automatically pick up the changes and then update the security rules in the the Firestore emulator. So it allows us to like do quick like and fast like testing locally. So here let's try to fix our security rules to like match the requirements. So allow read because we allow reading for like read on documents, and but then we allow write if false um, because we don't want anyone to write documents that we don't collection. So these are just simple examples. For actual apps, this will be like more complicated, but you can still write unit tests um, for those. So it's important to like write unit tests for security rules because as you write more, as we add more features to our app, we want to make sure that the parts that we've already secured beforehand remain secure after we add the features. We don't want to accidentally modify our security rules that will like expose some information that should remain private, right? So yes, that's why we write unit tests. After we fix our firestore rules to the correct rules, um, the emulator will pick up the changes automatically, and the next time we run our tests, um, both tests will be passing already. So that's great. And yes, so we've only shown the Firestore emulator now. I mean this stuff, but the Firebase emulator suite supports other emulators also for other services like Firebase authentication, the real-time database, which is Firebase another database service. We also have you also have the emulator for cloud functions and Firebase hosting and PubSub. So depending on your app and what you are using in Firebase, you can run their corresponding emulators locally for during development. And yes, that's pretty much it. So this talk covered like structuring data in Firestore and securing them with security rules and the things that we can check in the security rules. And we also wrote unit tests for our security rules to make sure that they're working as expected and can run them in the Firebase emulator suite. And that's pretty much it for this talk. Thank you for listening to the Firebase Cloud Firestore session. Thank you.
Okay, give it up again for Arnelle Balane. Yay! Anyway, what an insightful session on software development, Mr. Balane. And thank you so much again for taking some time off your busy schedule to talk to our audience here at WorkBrain today. And I'm sure the audience has some burning questions they want to ask. So, before anything else, don't forget to register and create a WorkBean account at workbean.co by 12 noon today. Okay, because that's your official registration and that's how you'll get your crushed ice. Just a friendly reminder. Um, Please make your WorkBean account at workbean.co uh, by 12 noon today. Okay. So anyway, um, let's get on to the questions. Any questions here?
Uh,
Ayun,
I'm
we have our
checking
first
the
question.
chat. Should I read the questions? Okay, I can read the questions.
Yeah.
Okay, so here's a question from Prince. Hi, Prince. Hello, why do you use Firebase instead of other NoSQL like Mono or Cassandra? What is the edge of NoSQL to SQL and vice versa? Okay, two questions. Thank you for the question, Prince. So first question, why do we use Firebase instead of other NoSQL like Mono or Cassandra? Yes, so there are things in Firebase also. So Firebase itself is not just Firestore. Firebase is like a collection of services for like can use for like web and mobile development. So I guess the question can be replaced to whether we use Firestore instead of Mongo or Cassandra. One nice thing with like using Firestore, it's integrated with the other um, Firebase services already if you need to use them. So, for example, Firestore is integrated with cloud functions, so we can do things like if someone writes data to Firestore, we can run a cloud function and respond to that to do like other processing. So that's one thing. Also, if we're using NoSQL databases like Mongo or Cassandra, we also have to write our own backend, right, to communicate with Mongo or Cassandra. But Firebase is like marketed as like backend as a service, so you don't really have to write your backend anymore. You just interact with Firestore directly using the Firebase SDKs. So that's one thing. Why maybe if you need to interact, if you need to integrate with other Firestore services like cloud functions, what else are other Firebase services, notifications and other things like that, then use Firebase. Otherwise, if you have your own backend already and um, don't need to use the other Firebase services, then you can stick with other NoSQL databases also like Mongo, etc. What's the edge of NoSQL to SQL and vice versa? So like one main difference between them is like how they structure data, right? So SQL is organized in tables, and each table has a schema, which is like the description of what fields are should be there and what the types of those fields. And then each data item is like stored as a row in the table, and each row should match the schema. Whereas in NoSQL, it's
Yeah.
very loose, it's not very strict. So there's no schema, everything is a document, which is basically a JSON that organized into collections. So what's the edge of NoSQL? At least for Firestore, not really familiar with the other ones that much. But with Firestore, one edge is that it's very, very fast because in Firestore, everything is indexed. So um, reading reading documents from like Firestore is really, really fast. Also because NoSQL is just a collection of like JSON document. They can be easily scaled like horizontally in case the app grows. Although with Firestore, we don't have to worry about the scaling part because Firebase will do that for us. Um, so that's its edge with NoSQL. Edge with SQL also, yes, there's a reason also. There's some things also that are good in SQL that NoSQL stuff that NoSQL databases can do. Things like if you want to do like complex queries, like for example tables, you want to join multiple tables, like aggregate a lot of data. Those can be easily done with um, SQL and NoSQL. It depends on the database. Firestore has pretty limited querying compared to SQL databases. And also, if you want to enforce like the schema part, let's say in your app, um, consistency and like the schema or your data is important, then that's easily done and enforced with SQL databases also. So yes, I hope that answered the questions. Thank you, Prince. I don't know actually where to find the other questions. There's a slide. Wait, let me open. Okay. Wow, so many questions. Okay. I'm just going to go through them one by one. Okay. So first question from Anonymous. Okay, all the questions are from Anonymous. How can you start when you are intimidated from the other talented individuals? Huh. Okay, good question. That's not really related to Firebase. How do you start? I think, I mean, at least for me, just don't compare yourself to the other individuals. Okay, please refer to the recent ones. Okay, so yeah, after this. Um, I mean, just don't compare yourself to other individuals. Just worry about like how you're learning, if you're how you're learning new stuff. So comparing yourself to other individuals, I think, is like an easy way to like discourage yourself because some individuals that you compare to are usually already like better at something. So that's why you compare yourself to them in the first place. I think, at least for me. So just don't do it. Um, worry about how you learn, what you're learning, and how you're doing it and what you're doing it. So, and okay, recent questions. When to use SQL or NoSQL? Is there a specific kind of app or category to integrate SQL instead of NoSQL or vice versa? Yes, I think I already mentioned this earlier, but yes, when to use SQL, if you want to perform like very complex queries, that's easily done with SQL because SQL can do like joins, inner joins, outer joins, things like that, sub queries. So complex queries can be done with SQL. So if that's what you need for your app, and that's how your data is like organized in the first place, then SQL. For NoSQL, I usually for just like not really structured data. So, um, for example, in Firestore, you can store data even though they don't have the same fields. So if allows you to change your app really fast also because you don't have to write database migrations. So I think yes. Next. Hi, Arnelle. This is insightful. Yes, thank you. I am new to programming. Is Firestore easy to understand for a beginner like me exploring on database? Do I need to learn SQL? Yes, to use Firestore, you don't need to learn SQL because Firestore is a NoSQL database, so you don't really need SQL for that. But if you're exploring databases, I think it will also benefit you or us in general, if you're familiar with SQL, maybe at some point you will be doing a project that will use relational database, so at least you already know SQL. but SQL is not required for Firestore. And Firestore is easy to understand for beginners. Yes, it's actually very easy because you just use the Firebase SDK to interact with um, Firestore directly, so you don't have to write. You just call functions, pass in the data they want to store, and then it just works. And one nice thing with Firestore also is that it supports real-time capabilities. So if one user like adds something, it can be displayed in real time to other like connected users also. It's can I integrate Firestore with AWS, or is it strictly for Google Cloud? Yes. It depends on what you mean, what kind of integration you want. But normally, Firestore it only triggers like, for example, with the function stuff, it can only trigger like Google Cloud functions or Firebase Cloud functions. But Firebase in general, not just Firestore, can I think integrated with like other external services also, especially when you call those services from Firebase Cloud Functions. So yes, Firebase, as I mentioned, is a collection of a lot of different services. One of those is Cloud Functions. So from Cloud Functions, we can call other um, services. For example, if you want to send emails using AWS simple email service, we can call that within our cloud functions, and then the cloud function can be triggered automatically by Firestore because Firestore is integrated with Firebase Cloud Functions. So yes, I think so. Not Firestore directly, but Firebase in general. Is it possible to convert our current database to Firestore? Huh. So I'll just assume that current database is a relational database. I'm not actually familiar if there are tools to like automatically import um, uh, relational databases into Firestore, but I think it depends on how like complex your database is already. If and how you're using, how you're querying those data. So I think you can answer that because you know your database more. So I would suggest just check your data, how it's stored, like how the relations, what's like how the different tables are related to each other, and then check in your app, like do an assessment in your app, like what kinds of queries you're performing. So if those queries are just simple like one-to-many queries and you're not really using a lot of complex queries, I think it would be possible. But if you're using a lot of like complex SQL, then that might be difficult. Next, any advice for those who want to shift their career to programming? What type of software we need to learn first? Thank you. Ah, any advice? Uh, okay, what type of software we need to learn first? So it depends on what, because programming is like a very broad term. So you can either be like a web developer like me, or like you can be mobile developers like Android devs or iOS devs, and you can be like backend dev where you do where you code in programming languages like Python or like Node.js or Ruby, things like that. So I think first, my advice would be like programming is too broad, so like try to identify what kind of programming or like development you would like to do. Do you prefer, or like are you leaning towards building user interfaces that the users can see directly, or are you leaning towards like building mobile applications that you publish into the app store? So depending on once you've identified that, I think start with the fundamentals for those. So I can't speak for like the other kinds of development, but at least for web, start with like learning HTML, CSS, JavaScript, because those are the fundamentals for the web. Regardless of what other technologies you use in the future, those three will be like a constant thing. So um, yes, learn the fundamentals and then identify what kind of programming you want to do. And I'm told that I need one last question, so let me just choose um, an interesting questions. Um, I think the other ones are not related. Okay. I'm trying to look for questions that are related to Firebase. Shit, I don't have anything. Okay, kaya lang. Does using it require having prior knowledge of matter computer science? Does using Firebase? No, I don't think so. So I'm no. To do like to use Firestore or like to do programming in general, I don't think you need prior knowledge on math or computer science. They do help, but there are definitely great developers out there who didn't have math or computer science backgrounds. So it's definitely possible um, to be a developer without those backgrounds. So a lot of the people that I look up to, a lot of like the really great developers that I look up to, they don't have those backgrounds. They have like completely unrelated like fields before, and then they just shifted to development. So don't worry about